So now we are going to see that how to generate 2D Gaussian. So this syntax over here will create a matrix of 2 cross 2 size. Just because we are generating 2D Gaussian, so that will be 2 dimension. So that's why this will be covariance matrix, and that will be of 2 cross 2 size. So let's see how does this matrix looks like. So if you can see over here, this is how the matrix looks like. So the anti-diagonal element of this matrix are 0, 0. It basically shows that there is very less covariance correlation between the attributes or the dimension of this 2D Gaussian. So this is the expression of the formula of 2D Gaussian. This one is a covariance matrix, and this is the uh, mean vector, and this one over here is the x vector. So what we are getting is this x vector. Normally we do pass the x vector and then get a single y vector, which is kind of the 2D, which is the value of that 2D normal form. So, but using R MV norm, as I have told you already, the R thing is giving us the basically the distribution. So it gives me the distribution. So if I could show you, uh, this is the 3D axis. So over here we will have the value of y, and these are, let's say, x1 and x2. So given covariance matrix and the mean vector that we have specified over here, 2 2 is a mean vector, and sigma is a covariance matrix. So we'll get these values. So x2 and so x1. So these value will get as a answer, or as in matrix form basically. So we are going to get x1 and x2 values, and how many values we are going to get are 1000. So let's run this code. So as you can see, the BIVN variable contains this data. This is the data that we have generated using 2D Gaussian. Now, one thing that you should remember, please do install MVT norm package, and after installing that package, please use the required keyword or library keyword and include it within your program. Do not forget, because this our MV norm method is actually inside MVT norm package. So use the command install packages and so I have already installed that package. That's why if you haven't installed, then it will be installed in your system again. Do not forget to load, because just installing won't do your job. So okay, now we have seen BIVN. If we want to see how does it looks like, so we will use this command. Okay, so it basically generates the contour. So this is the contour of the Gaussian that we have just created. So and you can use the image command to visualize in such kind of heat map way. So this is the point where the mean is situated, and this is, you can realize this is the result of covariance matrix, the spread of this curve is. And using the perception command, PERSP, you can see this thing in a sort of 3D way. So here you can see how our 2D Gaussian looks like. So I can't rotate right now, but using the modify value of phi and theta, I think you might be able to rotate it. So okay, let's see. Okay, so now it's sort of top view. So you try changing the value of phi and theta and see what kind of view you are. And one more thing, these packages or these methods are the result of the MAS library. So you have to install or you have to load this MAS library. If this MAS library is not pre-installed in the R package, then use install.package command. But normally it comes pre-installed, so you just have to use the require or load library command. Okay, so now let's see how to generate the line in R. So this is the vector contains the value of 1 to 100. Now this is a simple variable, or in our linear model we are going to call it intercept. So we have decided intercept equal to 23, and m, which is the slope, is 0.56. So now we are generating a line, and if we plot this line, as you can see, so it's a straight line. Okay. Now what we will do is we will add some Gaussian noise to our already generated model. So this is the y value that we already got, and now we are generating a random Gaussian noise. So after generating a Gaussian noise, if we realize that, okay, what happens with the line, so see, okay, so this is how the our particles of the line are now distributed. So in this form, actually the data that you should model comes into to you, so that if you realize that, okay, you can fit it in a single line, it seems like that you can fit it in a single line, then you can generate a model that gives you the least square error, and then using those parameters you fit the line over here. We'll see that how to do it in R, but as of now you just consider that using this noise we can generate this sort of distribution. Another thing, when we decrease the standard deviation, then it actually doesn't give you that much of feeling that it came from a straight line. But if we decrease the standard deviation, it gives you the kind of nearest line structure. So let's decrease it to 5 and repeat the process again. So again, straight line, modify the value of y, see the plot. So here you can see it's now less deviated from the original line to which it belongs.